In this video, we're going to look at how to determine the current induced by a changing magnetic flux through a coil. So imagine, if you will, a coil of wire or a loop of wire, however you want to term it, embedded in a magnetic field such that nothing. A coil of wire embedded or immersed in a magnetic field. Let's ask ourselves a few questions now. The first question is this: Is there a magnetic flux in general? Right? I haven't even gotten to the changing part. Is there a magnetic flux? And the answer to that could be no. Right? The coil could be arranged in such a way that there is no magnetic flux. And if that's the case, then we're done. Now, we've got to be a little bit careful because we need to look at the system over a little bit of time, because it's possible for the instantaneous flux to be zero, and yet there still be some sort of change in magnetic flux. So, if a coil in a magnetic field is rotating twice every cycle, the flux is equal to zero. But hopefully we see that that's an instantaneous value, and hopefully we also see that the flux is actually changing over some amount of time. But if we look at the system over a certain amount of time and there's no flux, the coil is oriented such that there's no flux, then we're done. There's nothing to calculate here, so we can go on about our business. But assuming the answer to question number one is yes, we can ask ourselves question number two: is there a change in the magnetic flux? Again, if the answer is no, the flux is sitting still, or flux doesn't sit still, if the flux is not changing, then we're done. There's nothing else to ask ourselves. But again, assuming that the answer to both of these questions is yes, we can now go on to question number three. Let's ask ourselves now, is the change in flux negative, or is the change in flux positive? What am I actually asking there? Is the flux decreasing or is it increasing? Right? If the change in flux is less than zero, if it's negative, my flux is decreasing. If my change in flux is greater than zero, it's increasing. So now I ask myself, how is it changing? And what Lenz's law tells us is that the current is going to flow in such a way to counteract this change. Nature seems to hate change, at least in some situations. Right? That's not a hard and fast rule, definitely not a hard and fast rule. But in some situations, it seems to be an okay guiding principle. So what can we say here? If the flux is decreasing here, nature induces a current such that the flux is, or at least tries to be, increased. If the flux is increasing, nature tries to decrease it. I say tries because she never completely succeeds. This is an effort which is doomed to failure, but she does try. Once I have the answer to these questions, I just need to use the right-hand rule to satisfy the condition I arrived at in 4. I do that by examining what nature's trying to do, increase or decrease the flux, and compare that to the field producing the flux in the first place to let me know what direction my induced field needs to be. I think everything's easier with examples, so let's do an example. Here's my coil of conducting material. Let's put a B field into the page. We're going to completely immerse this coil or this loop in the field, and I'm going to let B be increasing in time. Okay? Now, let's ask ourselves this series of questions. Is there a magnetic flux through this loop? And hope we can see that, yeah, there is. In fact, in this position, it's maximized. The area vector of this loop is either out of the page or into the page. The magnetic field is into the page. At least by magnitude, then, the flux is maximized in this position. So definitely there's a magnetic flux. Now, is the flux changing? Well, yeah, the flux is proportional to the field. So if the field's changing, the flux is changing. Okay, now let's question number 3. Is the change in flux negative or is it positive? Is the flux decreasing or is it increasing? Well, if it's proportional to the field and the field is increasing, we got to say that the flux is also increasing, right? So that's increasing is here. Now, what does nature want to do? Question 4. If the flux is increasing, nature wants to decrease it. Right. Now, I should say that this flux is increasing. I'm pointing to decrease because this is what nature wants to do. Nature induces a field such that she tries to decrease the flux. Now, let's take that idea and look at the field. How do I decrease a flux that is coming from this field? The field is into the page. How do I decrease that flux? The only way I know to do it is to induce the magnetic field out of the page. Right? So the orange is the background field that's producing the flux. The blue is what I've arrived at by recognizing that nature really wants to decrease the flux. And so nature induces a magnetic field like this. Well, how does she induce a magnetic field? That comes from a current, which comes from the induced EMF. But as long as I've gotten here, I can tell you how the current flows, because now I just use the right-hand rule for fields. I've got a field that's straight. That's my thumb sticking out of the page here. And my fingers then will tell me the direction of the current. In this case, looks like the current flows counterclockwise. Let's do another example. Simple example. Let's take a long current carrying wire. But let's let I not be steady. I is decreasing. And above that, let me put a loop of wire. We'll make this one a rectangle. It doesn't really matter. Okay, fair enough. Well, let's ask ourselves the same series of questions. Is there a magnetic flux through this coil? And hopefully we see that the answer is yes. This is a current carrying wire. Therefore, it's going to produce a field. What direction is the field? Well, use my right-hand rule for fields. Thumb in the direction of what's straight, fingers in the direction of what's curved. In this case, the field is curved, so it looks like above the wire, this field is coming out of the page. So there's my magnetic field due to the current. Fair enough. Now, that's question number 1. Yes, there's a flux. Question number 2, is the flux changing? And yes, it is. The flux is proportional to the field, but the field is proportional to the current. So if the current is decreasing, the field is decreasing. If the field is decreasing, the flux is decreasing. So yes, the flux is changing. I've already answered the third question. Is the flux increasing or decreasing? It's got to be decreasing. The flux is decreasing. So what does nature want to do? She wants to increase it. How do I increase a flux due to a field that's coming out of the page? The only way I know how to do it is to induce a field also coming out of the page. Right? We got a field out of the page in the last example, but that's because the background field was into the page and we were working against it. Now I need to work with it because the flux is decreasing and I want to bolster it up. So I again induce a field out of the page. Right-hand rule for field again tells me that that current has got to flow counterclockwise.